Hello, welcome to my channel. I hope you're doing well, and I'm fine also. I'm doing great. And today, in this video, what I'm gonna talk about is um, electrostatics. This is my new start on the topic of electromagnetic fields, and I am starting with usual as usual. Everyone starts um, every undergrad starts the EMF course with electrostatics after reviewing the vector calculus and coordinate geometry part. So uh, from today onwards on EMF topics, I will discuss about electrostatics and then move to magnetic fields and electrodynamics. So as you can see, I have written some things beforehand, so I can explain a little faster. And so let's get started. So electrostatics is a phenomenon. uh, it is a it is a it is an effect of electric charges like electrons, ions, and anything that carries charge in it. So electrostatics deals with electric charges at rest. So when we are talking about electrostatics or static electric fields, we are talking about charges that are at rest, that are stationary at some point in space and time. So electrostatics deals with electric charges at rest and force fields that they produce. The force field is E, or the force Fe, or etc. So the charges may be positive charge or negative charge. So positive and negative charges have their effect in a region which is called field. Effect of anything in um, around a certain region is called field. So positive and negative charges have their effect in a region around them, creating static electric field which is generated by this. Electric field is a vector, obviously, there's no doubt about it. And one um, important point is that static charge distributions in any medium and any dimension creates time invariant electric field or static electric field. So electrostatics is time invariant, it doesn't change with time independent. So that's general introduction to electrostatics. So positive charges have their electric field, their flux outward from them by convention, and negative charges are opposite of positive charges, they have their flux, force field inverse to them. And when a positive and negative charges are um, in close proximity, they create an electric field which is a vector, obviously. From positive to negative, the field is from positive to negative. So electrostatic fields are everywhere in nature. So among many uh, applications and examples, I have written some. So ESF, meaning electrostatic fields, are cause of various physical phenomena like lightning, corona effect in power system, high voltage lines, uh, CRT beams, cathode ray tube beams, the thing we see in oscilloscopes and cathode ray tube televisions. the static images that is formed on the uh, screen is formed by static electric charges shot from the tube. So the CRT beams are cause of electrostatic field charges. Then the um, example one of the most general example of electrostatic fields is in the application of electrostatic fields is in electric power distribution and transmission. Then electrostatic fields are seen in X-ray machines. The effect of electrostatic fields are also used in displays like LCD, LED screens. In inkjet printers also use electrostatic fields for their operation. There's also electrodeposition. Various medical equipments use electrostatic fields in their operation, which many of us don't realize or observe. Electrochemical machining and all computer peripherals are manufactured using ESF or electrostatic field principles. So electrostatic field is very important phenomenon. It's an effect. It's a natural effect that is used to design and manufacture uh, one of the most sophisticated instruments the human civilization has ever made. So it is a very important uh, topic in electromagnetic fields altogether, and we have to understand a student like me and yourself, the viewers who are watching or are interested in EM fields. So electrostatics is a very important topic. So electrostatics is governed by two laws of force. One is Coulombs law and the other is Gauss's law, and I'm gonna discuss this right now. So as I was saying, so electrostatics is governed by two major laws for charges and charge electric charges and electric charge distribution, especially at rest. So Coulomb's law, first I'm going to discuss about Coulomb's law and all its special cases in my upcoming videos on EMF, and then I'm gonna sequentially go to the law, go to Gauss's law. So first Coulomb's law. So Coulomb's law is similar to law of gravitation. It's a law of force, so which states that considering electric field, which is static electric field in a vacuum, the force between 2 point charges q1 and q2 is F equals to k q1 q2 by r square, where r is the distance between q1 and q2. So the force is felt by both the charges q1 and q2, and the force, which is the Coulombic force, which is only applicable to point charges, uh, is it is proportional to the two charges, their magnitudes, and is it's anti-proportional to the distance squared, which is the distance between the 2 point charges, and k is the proportional constant, which is 9 into 10 to the power 9 meter per force. Formula for k is 1 by 4 pi epsilon o. Epsilon o is the permittivity, electric permittivity in vacuum. So which is 8.854 into 10 to the power minus 12. Coulomb's law This is a very important point, that Coulomb's law abides by superposition principle. Now here, so the force is obviously a vector, and for charges and charge distribution, um, there the force uh, doesn't only apply to two charges, it can apply to as many charge as there are. So we have to generalize the force, the coulombic force between charges. So because Coulomb's law, the law for force, um, abides by superposition principle, we can say that for q1 q2 to qn charges, which are distributed at distances r1 r2 r3 to rn, the corresponding distances for the charges q1 q2 to qn, the force on a test charge, say q it is a test charge, the force on that charge is the superposition of all the forces individually individually experienced by the test charge. So the net force on a charge experienced by the other charges is q by 4 pi epsilon o, the summation of the n charges, the in vector form, the full form of the generalized formula for Coulomb's law, the Coulombic force. So I'm gonna solve some questions to understand this equation, and before that I'm gonna talk about electric field. So we are talking about electric field E, but what is E? E is nothing but force per charge. So electric field is expressed in quantity by electric field intensity. Electric field intensity is is defined by force per charge, per test charge. Okay, so the formula for Coulombic force experienced by a test charge, say q, this is the formula. Now we're gonna uh, quantify the electric field. Electric field is quantified by the electric field intensity. So electric field intensity, which is also a vector. So electric field intensity is denoted by the same electric field E with its cap, so the direction arrow. So electric field intensity is expressed by E with cap or no cap, limit q tends to 0 f by q, or simply f by q. So force per charge, as charge tends to, the quantity of charge tends to 0. So this is the actual description of electric field intensity, and that's how we define an electric field, an electrostatic field in time and space. So if this is the formula, this is the relation of electrostatic field, then it can be expressed in terms of many charges in general. So in general, for many charges, electric field intensity, formula for electric field intensity is 1 by 4 pi epsilon o summation k equals to 1 to n qk, the charges which create the field and the intensity, field intensity by distance. So this is the formula for finding electric field intensity. It is very straightforward. It is just the force field by the charge itself. Formula is in vector form. So now what I'm gonna do is I'm gonna take some problems and solve it, and that will be it for this video. Okay, here the question gives the information of 2 point charges. One is 5 millicoulomb and the other is -2 millicoulomb. It is obvious because charges can be either positive or negative, and these two charges are located at 204 and -305 coordinates respectively, and this coordinate is in Cartesian coordinate system. So it asks to determine the field, the force field E, and the force field E on a point charge of 1 nanocoulomb at the Cartesian coordinate 1 3 7, and further it asks to find the actual force on the charge at that position. Okay, so let us first find the electric field intensity at this point. So first let us calculate distance. So our given r is 1 3 7 r1, distance from reference of the point charge 5 millicoulomb, say r1 is with. So the relative distance is r minus r1, the first distance, which is 1 3 7 minus 204, r minus r2 is 1 3 7 minus 305, which is, now we just have to calculate E in vector form. So all we have to do is plug the values. So this Q is the test charge, so 1 into 10 to the power minus 9 coulomb, and this is 4 pi into 8.854 minus 12 cross. So first is 5. So I have come to this point. So here I have just replaced the variables with their corresponding values, and this is what it looks like. And you can understand what this is the magnitude of the distance squared with the vector and the unit vector. So this looks like this, and I'm gonna just straight write the answer. Okay, so as you can see, I have derived the values of this relation. So um, this is the answer for the electric field intensity, and now I'm gonna find the force on this charge at this position. To find it, I just have to multiply this electric field intensity with this charge, and that's it. So after using the value, so here I had made a minor mistake. So here it will be 10 to the power plus 6. Okay, 10 to the power 6. So uh, after replacing the values, I have found uh, the value of the value of the force experienced by this point charge at this position, so which is this in millinewtons. That's it for today. I have just showed you only one uh, problem. In my coming videos, I will be mainly focusing on problem solving rather than the theory jargons. So stay tuned for those, and I hope you understood my video and this uh, problem solving. And that's it for today. If you like this video, please subscribe to my channel, and that's it. Thank you.